Hello, welcome to my new channel. In this channel, I'm going to make contents on different aspects of material science and hope you will like it. So today I'm going to talk about the famous XRD phasing problem or the phase problem of X-ray or diffraction technique. So first, I just want to introduce the technique XRD to you. If you're a material scientist, you already know it's XRD, X-ray diffraction, that uses X-ray to shine on any solid material to understand the crystallinity of the material. So it is the basic building block of crystallography. Now, just to make it easy for you, here I made a very interesting spaghetti marshmallow model, right? It's not, I tried to make a face-centered cube, crystal cube, but let's say your material has this, crystalline unit, or right, as a building block. The thing is, how do you characterize that? How do you understand that? So in that case, you use X-ray. So the X-rays identify these planes. They interact with these planes. What are the planes? See, these are the atoms, like these marshmallows here. These little marshmallows are like atoms. And these atoms, once they are oriented in a certain pattern or certain formation, they create a plane. So this is one plane, this is another plane. You have like 6 planes and there are planes inside depending on the position of the atoms. Now, the thing is, what XRD does, they interact with these planes, right? So imagine XRD is like a light coming in and interacting with these planes, and then it's like reflecting. We call it diffraction, but it's similar to reflection, but it diffracts when it is diffracted from different planes. Now let's say XRD1, it is coming in this direction, diffracting here, going in that direction, and another X-ray coming in here, interacting with this plane, creating another diffracted X-ray, right? Now you have 2 incoming X-rays and then you have 2 outgoing X-rays, right? Now, depending on the interference of these 2 outgoing X-ray, you will see, you will be able to figure out what's the difference or distance between these 2 planes. Now, I am using this just to show you, but it has some little bit intricacy in it. So what I'm trying to say, if you use X-ray, you can get an idea about atomic planes in that scale, in that atomic scale. Now, what happens, like if you understand the basic principle of interference, if 2 waves come and meet at the same phase. Now, when you measure the wave, there are 2 things. With waves, you have amplitude and you have the phase, that means the timing. Now, if 2 waves, they match or they interfere with each other or like overlap each other at the same phase, like let's say this is one wave, there's another wave, they interfere at the same phase, then you will have a constructive interference. However, if you have 2 waves, they're coming in a different phase, right? Let's just say this is one wave, there's another wave, then it will be destructive interference, and in that case it will just cancel out each other. So depending on how these X-ray waves are interacting at the detector, you will be able to figure out if there is a plane or not, right? So anyway, the phase problem is like with X-ray, you only get the amplitude information. You don't get the phase information. And this problem was first identified by the Bragg's family, the Bragg's law that is used to calculate the interplanar distance. So they figured out in 1915 in their own paper. And there is a paper about this whole phasing problem. I will just link it in the description for your reference. So yes, and this has been known for a century. Now, scientists have devised many ways to work with that, to get a solution for the phasing problem. And one way, like there are multiple ways, I'm going to talk about one way, which is known as the isoformous substitution. What it does, scientists replace one of the atoms with an heavy atom. Once a heavy atom is placed, it just changes the structure in a way that you see or notice the difference in the diffraction pattern. So by characterizing or comparing the diffraction patterns of modified crystal and your base crystal, you just you can figure out what's the phase is. I'm just making it very simple just for explanation, but it's not that simple. So you can look up, like there are other methods too, like direct methods, anomalous method. But the problem is these methods, they are very time consuming. They takes a lot of experiments to do to figure out what is the phases. It's like lots of trial and error just to hone in or like tune in the right phase. At this point, why am I bringing up this topic? Because recently there's a paper that came out, and where the authors, they use machine learning method to solve this phase problem. So in this machine learning method, what they are doing, very simply, they are training their model on thousands of materials data set. So once the model is trained on so many data set, and it can identify an unknown XRD pattern, and then it can properly assign the phase based on what the training is. So this is really exciting, and the paper, the model, they call it PHAI or Phi. I'm going to link the paper to the description if you want to check it out. So it has a very far-reaching impact because XRD is being used day to day in every industry. Like I work in cement and concrete industry, where cement producers use XRD and XRF every day to identify their the crystal phases in the clinker. On the other hand, the pharmaceuticals, they are always trying to identify the proteins they are synthesizing, characterize those materials. So it has a far-reaching consequence, far-reaching impact beyond what we can imagine. And it can if this machine learning method is proven successful, or if it can be replicated by multiple labs throughout the world, I think it's going to change this XRD landscape, and it's going to solve a century-old problem in a really positive way. So thank you so much for watching this video, and I will be bringing up more content like this. Feel free to share your thoughts and opinions in the comment section.